All right, algebra students. So today's lesson is on factoring special products. So if you remember back when we were multiplying binomials, there was one case where we could use a shortcut. So this case was called the sum and difference pattern. If you look back at the 7.3 notes, you'll see the sum and difference pattern. That said that if you had two binomials that were the sum, so a plus b, and the difference, a minus b, you could take a shortcut and take the first term squared minus the second term squared. Now, way back in 7.3 when we did that, we showed the box method and how you would actually have a positive first and second term, the positive product, and then a negative product, and then they would cancel out. So this pattern would always work with that sum and difference pattern. Today, we are going to learn the inverse of that. So we've been factoring, which is the inverse of multiplying, of course. Now you are going to have to notice when you have the difference of two squares, it factors into that sum and difference pattern. That's the big one you have to recognize today. The second pattern is that if you have a square plus 2 times both terms and then a second square, so if you see a square in both the first and last term, for example, x squared and 9, hopefully you can then see a pattern where you get the perfect square trinomial. If you were to factor this x plus 3 squared as x plus 3 times x plus 3, you would still be correct. So if you factored this our magic number way, you would get this. You can then simplify it to get this. All right, so using that first pattern, I see x squared minus 25. Obviously, x squared is a square, right? And I know 25 is 5 squared. So this matches that difference of two squares, and it's going to factor to x plus 5 and x minus 5. Really, the only work we need to show here is that the square root of x squared is x, and the square root of 25 is 5. This is your answer. All right, example B, 4z squared is still a square because 4 is also a square. If that were like 3z squared, it would not be a square. Even though z is squared, 3 is not a square, so that would not work. Because it's a 4, or if it were a 9 or a 16 or a 25, it is a square. The square root of 4z squared is 2z, and we know the square root of 1 is 1. So this, again, fits that difference of two squares pattern, and it factors to 2z plus 1 and 2z minus 1. Now when we look at this last example, even though we see y squared and 100, which are both squares, it is not the difference. So this is not the difference of two squares, it is a sum of two squares, so we can't factor it. All right, so now we're looking at the second pattern, the perfect square trinomial. I will tell you, you can factor this with the magic numbers. So we would do the same thing. What multiplies to 16 and adds to 8? That would be the square root of 16, 4. And then we use our shortcut. So n plus 4 and n plus 4. Same with this next one. We can use our magic number. 4 times 9 is 36, so what multiplies to 36 and adds to negative 12? That's going to be negative 6 and negative 6. So here would be your key, since those are the same numbers. You could split this into 4x squared minus 6x plus 9, or it's going to be that perfect square pattern. So if you get two numbers here, that might be a key to check. Is this a square? Is this a square? Yes, it is. And then we can use that pattern. 2x minus the square root of 9 is 3. So I can predict that pattern. For those of you that need to see the y, I'll break it into what we did in 7.6. So I'm splitting the middle term into my magic numbers. And then we factor by grouping. So 4x squared and 6x have a 2x in common. I have a 2x minus 3 left. 6 and 9 have a 3 in common. I see this plus in the middle and this minus over here. So I'm going to factor out a -3. So that -6 divided by -3 is +2. +9 divided by -3 is -3. Now my binomials match. And 2x minus 3 is what's left. So you can factor by grouping, or you can see the pattern. All right, last example. Let's see if you can try this by yourself. Pause the video, play it back, see if you got it right. I will set up the magic numbers. So what multiplies to -25 adds to 10. Oh, just kidding. The square root of 25 is 5. And if we do 5 and -5, it doesn't add to +10, it adds to 0. So here's another one that we can't factor. Okay, so here we are combining what we know again. We're going to factor the trinomial, and then it's equal to 0. So we're going to use what we learned in 7.4, our zero product property, and we're going to solve for the variables. So what multiplies to 9 and adds to 6? That would be 3 and 3. I see that this is a pattern, so I have a plus 3 squared. If you have one binomial squared, that means you are only going to have one solution. So that means a plus 3 has to equal 0. And of course, if we minus 3, a equals -3. All right, last one. This is the difference of two squares. I know the square root of n squared is n. I know the square root of 81 is 9. So I factor this to n plus 9 and n minus 9, meaning if that equals 0, one of the products has to be 0. If n plus 9 is 0, n is -9. If n minus 9 is 0, n is +9. On like a fast test, you might actually see this written even simpler. You might see it written as +9. That would be that square root of 81. Positive and -9 squared, both equal 81. All right, so here's a chart just simplifying everything we've learned with factoring, because I know it's been a lot. We've had like 4 sections on factoring polynomials. So basically, here is when you would use the perfect square trinomial. Again, you can use magic numbers. And here is where you would use the difference of squares. So the main difference between these two patterns is that this is going to have 3 terms and this has 2 terms, trinomial, binomial. The main thing they have in common is that the first and last terms of both special products are perfect squares. So if you see a polynomial and the first and the last are perfect squares, you know you can use a pattern.